In this section, we'll discuss inference for one proportion. For categorical response variables, we've talked about hypothesis testing already using a chi-square test for the 2x2 or R/C contingency tables. We've talked about Fisher's exact test if we have low expected cell counts. And we've also talked about McNemar's test for dependent groups. All of these are for more than one group of observations. What if we only have one sample of data? In continuous response variables, we had the one sample t-test. And also, what about estimation? We can do confidence intervals for continuous responses, but how about for categorical responses? If there's only one or two groups, we can also use z-tests and confidence intervals for proportions. In this section, we'll talk about the z-test for one sample, and then there will be another section with formulas for confidence intervals for two groups of independent and paired proportions. When looking at proportions, if we have one proportion, we'll do a one sample z-test, which we'll cover in this section. If we have two independent proportions, we can do what's called a two sample z-test for proportions, but this is equivalent to the chi-square test, which we've already covered, so we won't go into details on this test. If we have two paired groups, we can also set this up as proportions instead of a contingency table, and that's McNemar's test, which we've already covered as well. So we won't go into details on that test again. This section will just focus on the one proportion z-test. If you think back to the binomial distribution, we had a response that had only two possible outcomes, a set number of trials that were independent of each other, and that had the same probability of success for each trial. If we have large sample sizes, we can approximate this using a normal distribution with mean of n times p and standard deviation square root of n times p times 1 minus p. With the binomial distribution, we could find the probability of a certain number of successes out of our total number of trials by using the binomial formula or the normal approximation. But what if we're interested in the proportion of successes instead of the number of successes? When we talked about the central limit theorem, we also talked about how the sample proportion is a special case of the sample mean. So if all of our observations are zeros and ones, where 0 is a failure and 1 is a success, if we average those, or take the proportion of successes, those things are the same. So what we learned with the central limit theorem applies here. So we know that the sampling distribution of a sample proportion has an approximately normal distribution as long as certain conditions hold. And those conditions are that n times p is greater than 5 and n times 1 minus p is also greater than 5. Where p is the population proportion. The mean of this distribution is p, the proportion, and the standard deviation is p times 1 minus p over n, and all of that square rooted. So since we know that the sample proportion has an approximately normal distribution, all of the things we discussed about finding probabilities and p-values in this section of the normal distribution apply here as well. To find probabilities for proportions, we use a similar formula to what we've seen before. We have the statistic of interest, or the observed value. In this case, it's a proportion, and we denote it by p hat. We subtract the population value, and here it's p, the true proportion, and then we divide by the standard deviation. So this is if you're finding probabilities. For a confidence interval for one proportion, we have the same general formula that we've seen before. We have our sample value, here it's p hat, our sample proportion, plus or minus a multiplier. Here we can use 1.96 or another value from the z-table because we're assuming a standard normal distribution. And then we multiply by the standard error. The one sample test for a proportion, again, is similar to what we've seen before, but now we're just using proportions instead of means. Our null hypothesis is p equals p naught, which is some hypothesized value. So it may be 0.33 if you're hypothesizing that the true proportion is 1/3. It may be 0.5 if you're hypothesizing that the true proportion is 50%. The alternative would be p does not equal p naught, so whatever your hypothesized value is would go in there as well. And these can also be two-tailed or one-tailed tests, just like the ones that we've seen before. Our test statistic is a z value that's calculated as our sample value, p hat, minus the hypothesized value, p naught, divided by the standard error. This quantity follows a standard normal distribution, so we can look up our p-values on table 8.3. If we have a small sample size, we can use a continuity correction here, just as we did with the chi-squared test, and that is demonstrated in the formula here. Unfortunately, for one sample test, there's no procedure in SPSS that does the one sample test, and that's probably because they're not very common. So if we wanted to do a one sample test for proportion, then you would need to calculate that by hand.